5.6 trapezoidal approximations. Let's review some geometry. So what is a trapezoid? A trapezoid is a quadrilateral, meaning a four-sided polygon, with exactly one set of parallel sides. So you'll see that, that's not a good color here. You have exactly one set of sides that are parallel, and the other two are not. The parallel sides are called bases, and the other two sides are called legs. This also is going to have a height. I will draw it in here. And we'll call that H. So you need to know how to find the area of a trapezoid, which is pretty easy. All I've done, if you look at my picture below, I just draw a diagonal, and that creates two triangles. So if you can find the area of the two triangles, you will have found the area of the trapezoid. And basically that's what this formula is. Eventually you can memorize this formula, but if you remember where it comes from, it's not going to be hard to memorize. So I'm going to give these bases a name. Base 1 and base 2, since they're different. Base 1 and base 2. And don't forget, we still have a height. The height from top to bottom is going to be H. So I'm taking this one and flipping it to get that. So if you see that, this is base 2, and this is my original base 1. So this triangle here, I just moved it straight down here. Now, what are the heights of these triangles? Well, they both have a height of H. So I'm going to call this H, and the height from here to the bottom here is also H. They both have the same height. And everyone remembers the area of a triangle, so I'll do area of triangle 1. It's 1/2 the base times the height. And the area of triangle 2 is 1/2 the base. Ooh, I should have renumbered these. Whoops. The base times the height. Well, if you want the area of the whole thing, the total area is the area of the first one plus the area of the second one, which is 1/2 base 2h plus 1/2 base 1h. And you'll notice they both have a half and an h. So if we factor that out, we're going to get b2 plus b1. And the final formula, I'm going to manipulate it slightly. And so it's like a triangle, 1/2 base times height, except now we're dealing with two bases. So when you do these, you could actually break them up into two triangles and do them separately, or you can just combine them and do one formula. It's probably wise just to remember that formula. It's not too hard to remember if you understand where they come from. It's just 1/2 base times height of two triangles, and they both have the same height, so it's pretty straightforward on that. So that's the area of a trapezoid. The trapezoids we're going to see in this class are not going to be laid down horizontally. So if we call that base 1 and that base 2, and this is the height, when I rotate it, this will be base 1, that'll be base 2, and this will be the height. But the height is going to be the width when we rotate it. So this is going to be the width. And what you're going to see, that's going to actually be delta x. It's going to be the change in x because the width is the change in x. Just like when we did Riemann sums, the width of our rectangles were delta x. And the same thing here. If you see it's a trapezoid, the only difference with a trapezoid, you're going to have an extra piece on top, which you didn't have with the Riemann sums. So that's going to be the difference. And technically, if you totally forget the trapezoid formula, you could do the area of this rectangle down here, and then you could separately do the area of this triangle up there and add them together. You could do it that way also. It's going to take more time that way, but very doable. You don't have to use that trapezoidal formula as long as you get the area correct. So how are you going to apply this? So here we have a curve called f of x. And instead of doing rectangles, we're going to do trapezoids. So if you look at this trapezoid right here, you're going to see it's pretty. It's a lot more accurate than a rectangle. Because if I did a rectangle, left hand, it would be there, and I have all that extra piece there. And if I did a left hand rectangle, I'd be down here, and I'm missing all of that. But when you do a trapezoid, that is much closer to the actual. So in general, the trapezoid is closer than a left hand or right hand Riemann. That's why we might use it. And a couple of other notes. If you see this is concave down, like it is here, you're going to notice the trapezoid is going to be less than the actual. And on the section where it's concave up, the trapezoid is going to be bigger than the actual. So just a food for thought. So how would we do this? So if you look at this, we have a bunch of areas, and we have to add them up. And how am I going to do this? I guess I'll call this x1, x2, x3, x4, x5, x6. I'll kind of set this up, and it might confuse you because this first one is not going to look like a trapezoid. But technically it is a trapezoid where the base here is 0. And so you will get the right answer even though it is a triangle. The trapezoid formula works for the triangle. Now, let's just do this. So the area 1 is going to be 1/2 the base. The base will be x2 minus x1. Okay? That's the base. And the heights, or I just kind of confused you a little bit. The heights are actually going to be our bases. When I say the base, I should have said the width. The height is going to be B1 and B2. How do we find those? I'll show you that in a second here. But the width, so here is the width. I subtract these x's to get the width between those two. So that's the width. But of our triangle is the base. And the sum of the heights, here's where it's going to get weird on you. And let me, you know what? Let me do it in the form I had earlier so it's not so confusing. So the final formula we had is 1/2 the sum of the bases times the height. Well, now it's going to be 1/2 the sum of the bases. Here's a first base and here's a second base. So the first base, let me scoot this over even more. The first base is going to be the function's height at x1, and the second base is the y value there, which is the function at x2. So that's f of x2. So to get the height of the second one, I have to add f of x2. And so this is 1/2 the sum of the bases times the width. So let me be a little more explicit here. This will be B1 plus B2 times delta x. Delta x is the distance from here to here again. What's B1 and B2? Well, it's the height here and the height here. What's the height, y value at x1? It's f of x1. What's the y value here? That's going to be f of x2. So that's why we have that. We will continue down the path here. Now, we're going to look at area 2, which is x3 minus x2. So this is the width. So it's x3 minus x2. But what's the height here? Well, that's going to be f of x2. So it's going to be f of x2 for the height there. And what's the height here? Well, that's going to be the y value. F at x3 is the height at that point. So I'm going to put f at x3. And we're going to continue down this path. For the third one, the width here is going to be x4 minus x3. The heights, this is going to be the height at x3. So it's f of x3 plus f of x4. Because the right-hand side height is from x4, that's f of x4. I think you get the pattern here. So the area of the fourth trapezoid is 1/2, and that's going to be f of x4 plus f of x5, and the width is x5. I don't know why my pen stopped working there. It's going to be x5 minus x4. And the last one is going to be using these two. So it's going to be f of x5 plus f of x6. And it's going to be x6 minus x5 to get the width. Now, I'm not going to write this all out, but the next thing you would do is you would add up all 5 of these to get your total area. So that will get you the approximate net area under the curve. And this is called the trapezoidal approximation. It's more accurate than the left hand or right hand. So that's why we would do that. A lot more work, but more accurate. So we're going to do 3 examples of different types of trapezoidals you might see. So the first one is going to be from a table. This actually appeared on the 2011 AP test. This was the question number 2. They give you a table of values. And clearly this is time in minutes. What's H? We have to read to get the description. So you have a pot of tea cools. The temperature of the tea is modeled by H. So H is the temperature of the tea. That's what H is. Time from 0 to 10 in minutes. Where T is measured in minutes, temperature H of T is measured in degrees Celsius. That's all given here, degrees Celsius in minutes. And you have select values of the temperature H of T at different times. So part A, use the data table to approximate the rate at which the temperature of the T is changing at time T equals 3.5. So when you see this word here, the rate, you need to think derivative. And normally to find the derivative, you need to take the derivative of the function and plug in 3.5, but we don't have the function. So how do we do that? And that's why they said approximate. So let's look at what they really want. So I graphed the points for you. You don't have to. This is a visual for you to understand what's happening. And as I connect these points, it looks like that's my function. And I just covered those points. I smothered them. Let me go back and unsmother them. Let me make them bigger first and then use a different color so you can kind of see what's happening. It appears that's the curve. So what is the derivative? You should know it's the slope of the tangent line. And they want it at 3.5. So they want the slope somewhere around here. And how do we find the slope of the tangent line at that point? That's the question. So if you look at this graph, the obvious answer is to find the slope between these 2 points. If I find the slope between these 2 points, let me change the color there. If I find the slope between those 2 points, that's pretty darn close to the slope of the tangent line. So that's how I'm going to do it. I'm going to use the average rate of change to approximate the instantaneous rate of change, and it makes sense to use the 2 points closest to the point I'm approximating. Now, technically, could I use these 2? It would approximate that, but not the wisest. Could I use these 2? I could, but it's not as accurate. So I'm going to use the 2 points around. So part A, I'm going to say h prime at 3.5 is approximately equal to the average rate of change. So the change in y is h of 5 minus h of 2 over 5 minus 2. And h of 5 is 52, h of 2 is 60 over 3, negative 8 over 3. So I get the answer of negative 8/3. The units on that, let's see. Does it ask for units? It actually doesn't ask for units, I don't see. So be careful. If you wanted to, well, h is measured in degrees Celsius and t is measured in minutes. So you could say degrees Celsius per minute. That's my answer for part A. Now, part B is the trapezoidal. Part A was more of a review of chapter 3. Or actually, yeah, chapter 3. Chapter 3 and 4, kind of. Using correct units, explain the meaning of that. Use trapezoidal sum with 4 subintervals indicated in a table to estimate. Okay, so part B, I'm going to need some room on this too. I can't move that picture. Oh well. I'm going to have to write really small. Or write in multiple lines, which I don't want to do. So how do I do this? I'm going to use the formula from the previous page. I'm going to do down here. 1/2 the sum of the bases. Well, if you look, the bases, that's going to be my first base, and that's going to be my second base. So it's going to be the function at those 2 points, which are 0 and 2. So it's going to be h of 0 plus h of 2. And then the width, it goes from 0 to 2, so the width is going to be 2. My next interval is going to go from this point to that point, which is 2 to 5. I'm going on this interval. So the same formula, 1/2. The bases will be the function at 2, the function at 5, and the width will be 5 minus 2, or 3. And since I'm running out of room, I'm going to start on the next line. The third interval will be from 5 to 9. So it's going to be 1/2 h of 5 plus h of 9. And the width is going to be 9 minus 5, so it's going to be 4. And then the last interval will be from 9 to 10. So 1/2 h of 9 plus h of 10. And the width is from 9 to 10, which is 1. Now I need to actually plug in values. So h of 0 and h of 12, the y value here and here is my 2 bases. They are my 2 bases, so it's 66 and 60. And the width was 2. Now I'm doing the next one, which is from 2 to 5. H of 2 and h of 5 is going to get me 60 and 52. So that's going to be 60 plus 52, and the width was 3. Can I fit this all? I'm going to go over onto my graph. I don't mind. So h of 5 and h of 9, I'm doing this interval from 5 to 9. So that's going to be 52 and 44 are going to be the bases here. So 52 plus 44, and the width of that was 4. And my last one is going to go from here to here, 9 to 10. Those values will be 44 to 43. And the width of that was 1. So let me do units. And let me show you how we do units. H of t was measured in degrees Celsius. dt is time, and that's measured in minutes. And if you look up front, so you need to recognize what this is, the 1/10. And wow, I butchered that. I put a half in front. That's supposed to be a 1/10. What is that 10 down here? Well, if you look, this is the average value formula. It's the integral divided by the width. The width is how wide this is. That's in minutes. So that units here, that 10, is minutes. And the minutes cancel, giving you degrees Celsius. So all this, saying all this, these units are degrees Celsius because they asked for units. And technically, that is my answer. I don't have to simplify it. You're not required to simplify an answer. In fact, you shouldn't. Now, I'll show what you could do. I could say, let A equal this. Okay, so I've defined all of that as A. If you were to simplify this, you would get the answer of 52.95. This is actually a calculator question, so you could pop that in your calculator. But, oh, I totally messed up. This is a big danger, and it might happen to you. That 1/10 in front. To say this is equals, technically I'd have to divide this whole thing. Now, it's on 2 lines, so I could divide by 10. So that whole, okay, how am I going to divide that by 10? I'm going to put a 1/10 in front. And then here, I'm going to divide this whole thing by 10. And so then if I simplify this, I get 52.95 degrees Celsius. Now they asked for us to interpret this in the context of the problem. So this is the average value of H. What's H? The temperature of the tea. So you'd have to say the average temperature of the tea in degrees Celsius was 52.95 from time t equals 0 to 10 minutes, or over the first 10 minutes, however you want to say that. So you can say the average temperature of the tea is 52.95 degrees Celsius for the first 10 minutes. And that would be the answer to that question. Let's keep going. We have 2 more examples. So that's from a table, and that's a very common way that it will appear, often on FRQs and on multiple choice. So here's another way. You might be given a graph of a function. So f of x represents the rate at which rain is falling in centimeters per day. So this is a rate, meaning it's the derivative of the amount of rain. Okay? So this is an important concept. Let A of t equal the amount of rain, then A prime of t would be f of x. It's the rate of the amount of rain that's falling. So centimeters per day, how much rain is falling. So at exactly time 0, it's 4 centimeters per day. 2 days later, it's 6 centimeters per day. On day 4, it's 6 centimeters per day. On day 6, it's raining less, 4 centimeters per day, and it's changing throughout the time. So that's kind of what f of x is. It's the derivative of the amount of rain. Now, they want you to approximate the amount of rain that's fallen over the 10-day period. So let me show you why this works. And this is a very important concept, fundamental theorem of calculus. If I go from 0 to 10 of a prime of t dt, the antiderivative of a prime is just a of t, and that's going to be a of 10 minus a of 0. Now, look, what is this? This is the ending amount minus the beginning amount. If you take the end amount, subtract how much you began with, it gives you the change in the amount of rain. So now, looking at this in the big picture, this is the change in the amount of rain from day 0 to day 10, and that would give you the amount of rain that's fallen. Because if you took the amount at the starting and the amount at the end, and you compare those, it'll tell you how much change there's been in the amount of rain. So it tells you how much rain has fallen. Important concept. You integrate the derivative of something, it gives you the change in what is the derivative of. So how would you estimate the amount of rain that's fallen? You would integrate f of x from 0 to 10 because f of x is a prime. So I would integrate from 0 to 10 f of x dx, and I'm going to approximate this using a trapezoidal. Now, just to make our lives easier, let's change it to over the first 6 days and not 10, because we are going to just have too much calculations and we're going to run out of room, and I think you're going to get the idea without this. And I didn't say, let me see. Usually they'll tell you how many subintervals. I should have said 1, 2, 3, using 3 subintervals. I didn't say that. So we'll say using 3 subintervals. So it's going to be from 0 to 2, 2 to 4, and 4 to 6. So it's 1/2. And my two bases, here's my first base, here's my second base. It's going to be f of 0 and f of 2 will be my bases. And my width will be 2 minus 0, which is 2. And my next interval is going to be from 2 to 4. My first base is f of 2. My second base is f of 4. F of 2 plus f of 4. And the width again from here to here is 2. And the last interval is from 4 to 6. The base 1 is 4 at 4. Base 2 is at 6. So it's f of 4 plus f of 6. And the width, again, is 2. So now, to continue on, how do I get f of 0? I look at my graph. It's 4. And how do I get f of 2? That's 6. So it's going to be 4 plus 6. And then how do I get f of 2 and f of 4? From the graph, f of 2 is 6 and f of 4 is 6. They both are 6. And for the last two, it's f of 4 and f of 6. That's going to give me 6 and 4. So it's going to be 1/2 6 plus 4. And the width of that, again, is 2. That would be fine if this were FRQ. If this were a multiple choice, you'd have to find the answer that matches. And what's nice, 1/2 of 2 is 1. 1/2 of 2 is 1. 1/2 of 2 is 1. Those all cancel out. I get 10 plus 12 plus 10. And this one's the easy 32. And that's my trapezoidal approximation. So the net area is about 32, but that represents about 32 centimeters of rain in 6 days. Actually, this is from here to here. That's a lot of rain. It's more than 10 inches, so that would be like a downpour. So that's example 2 when you have a graph. Example 3, you're only given a function. This on the right, they don't have to give that to you. I drew that in there to help you visualize what's going on. So we're going from 1 to 3. Here's 1. Here's 3. And they want 4 equal partitions. So if you cut that in equal parts, you're going to get there and there. This will be 1, 3/2. Let me back up on this and get a smaller pen size. That's 3/2. This will be 4/2, which is 2, 5/2, and 6/2, which is 3. So that's my picture. Okay, there are my 4 trapezoids. So to estimate the area under the curve and net area, you integrate from 1 to 3 of your function. So 1/2, the first partition, the bases, it's going to be at 1 and at 3/4. So it's going to be the function at 1 plus the function at 3/4 to get each base. And the width between 2, the width's always a 1/2 in all those. Plus, the next interval is going to go from 3/4 to 2, f at 3/4, f at 2, and the width of that's 1/2. And the next 2 is going to be 4/2 or 2 and 5/2. So it's going to be your function at 2 and your function at 5/2. And the width of that is 1/2. And if I can squeeze the last one in, it's going to go from 5/2 to 6/2 or 5/2 to 3. So it's going to be your function at 5/2, your function at 3, and your width is 1/2. All right, now the next step is to find the value of the function. What's f at 1? Well, I plug in 1 here, so that's going to be 1 squared. And then f of 3/4, well, it's going to be 3/4 squared. And the width between is 1/2. Next one, I'm going to be 1/2, but it's going to go from 3/4 to 2, so that's going to be 3/4 squared plus 2 squared, and the width's 1/2. The next one's going to go from 2 to 5/2, so it's going to be the function at 2, which is 2 squared, and then 5/2 squared, and the width's 1/2. And the last one's from 5/2, so it's going to be 5/2 squared plus 3 squared, and the width's 1/2. All right, so I'm going to combine all these. That's going to be 1/4. Every pair you're multiplying a 1/2 and a 1/2, so it's going to be 1/4. Now I'm going to pull that 1/4 out in front because they all have that 1/4. So what am I left with? 1 plus 9/4. 9/4 plus 4. 4 plus 25/4. And 25/4 plus 9, what just happened? So each of these have a 1/2 times 1/2. So they all have this 1/2 times 1/2, which is 1/4. So I just pulled out in front. I factored it out. 1 squared is 1. 3/4 squared is 9/4. 3/4 squared, whoa, those are supposed to be halves. I just realized. These are halves. So 3/2 squared is 9/4. 2 squared is 4. 2 squared is 4. 5/2 squared is 25/4. 25/2 squared is 25/4, and 3 squared is 9. Now I'll just keep going. Now technically you could have stopped here. You're done. But if this were a multiple choice, you'd have to get a simplified answer, so let's keep going. I'm going to need a common denominator. So I'm going to make these have a common denominator of 4. That'll be 4/4 plus 9/4. To get a 4, I need 4/4. That's 16/4. And similarly, that's going to be the same as that, 16/4. And the last one, that's a 9. So if I do 4/4, it's going to be 36/4. Let's keep going. I don't need a parenthesis there. That's going to be 13 fourths, 25 fourths, 41 fourths, 20, 50, 61 fourths. Can I add these? Let's see. That's 102, 107, 127, 130, 140. Equals 140 over 4. That's going to be 70 over 2. 35? Is that right? Oh, wait a second. I forgot the 4 on the bottom, Yoshida. So there's a 4 there. So it's actually 16. I can save this. I can save it. I didn't totally blow it. And that'll be 70 eighths, 35 fourths. That's 8. That's 32 and 3/4. Dun, dun, dun. That's my last example. We're done.